You know that perfect little swirl of hair you sometimes see on a baby's head? Well, it turns out that tiny little cowlick is the perfect real-world example of one of the most ridiculously named theorems in all of mathematics, the hairy ball theorem. And I promise, despite that name, this is a seriously fascinating piece of math with some truly mind-bending consequences.
So let's just get right to the heart of it with a simple question. Imagine a ball that's completely covered in hair. The challenge is this. Can you comb all of that hair down perfectly flat so that not a single hair is sticking straight up? I mean, it really feels like you should be able to, right?
All right, let's dive into this hairy situation. We'll start with the informal version of the problem, just to kind of build our intuition for the real mathematical puzzle that's hiding underneath.
Okay, so if you try the most obvious thing, combing the hair in a nice, smooth circle around the middle, kind of like the Earth's rotation, you immediately run into a problem. You end up with a swirl at the top pole and another one at the bottom pole. These are our cowlicks, points where the hair literally has nowhere else to lie flat, so it has to stick up.
And here's the thing. This isn't because you're bad at combing. This is the theorem itself in a nutshell. It is a mathematical guarantee. No matter how you try to comb it, no matter how clever or complicated your pattern is, you will always be left with at least one tuft of hair sticking up. It's just completely unavoidable.
So why on earth do mathematicians care so much about combing hair? Well, of course they don't, but they care a lot about what the hair represents. And the real power of this theorem is how it shows up in the real world, where that little tuft of hair becomes an unavoidable glitch or some other strange physical phenomenon.
Okay, check this out. Imagine you're a video game developer and you need to make an airplane fly around smoothly. Easy enough, right? The nose of the plane has to point along its flight path. But wait, what about the wings? How do you orient them? You need a rule, a continuous rule, that picks a wing direction for every possible direction the nose could be pointing. And this is where our hairy ball problem sneakily reappears.
Here's the connection. The set of all possible directions the plane's nose can point in is mathematically a sphere, and assigning a wing direction at each point is exactly like combing a hair on that sphere. So the hairy ball theorem guarantees that any simple continuous rule you come up with is doomed to fail. There'll be at least one direction where the plane's orientation just glitches out and jumps erratically.
And this theorem's reach is surprisingly huge. Think about wind blowing across the surface of the Earth. At any given moment, the theorem guarantees there's at least one spot on the planet where the horizontal wind speed is zero. The eye of a cyclone is a perfect example. Or what about radio waves? It's physically impossible to build an antenna that sends out a perfectly uniform signal in all directions, because the electromagnetic fields would end up violating this very theorem.
Okay, so we've seen the fun analogy and the strange real-world glitches. Now let's lift the hood and look at the actual formal mathematics. It's time to translate our hairy ball into the rigorous language that mathematicians use.
So instead of talking about hairs, mathematicians talk about a tangent vector field. It sounds complicated, but it's just a way of saying that we assign a direction, a vector, to every single point on the sphere. And that vector has to lie flat against the surface at that exact point, just like a nicely combed piece of hair. And here it is, the official hairy ball theorem. A continuous field just means there are no sudden breaks or jumps. A zero vector is our tuft of hair. It's a point where the hair has zero length and no direction, which basically means it's sticking straight up. The theorem simply says that this is a guaranteed feature of any such field on a sphere. Now for the absolute best part. How can we be so ridiculously sure this is always true? Well, we're going to use one of the most elegant tools in math, a proof by contradiction. We're going to assume the impossible is actually possible, and then we're going to sit back and watch as logic itself completely falls apart. So here's the game plan. First, we're going to pretend that we succeeded. We have a perfectly combed sphere with no hairs sticking up. Second, we'll use that perfect combing to define a motion that flows every point on the sphere along its hair. Third, we'll see that this motion actually turns the entire sphere inside out. And finally, and this is the key, we'll show that this outcome leads to a flat-out logical contradiction which forces us to admit we were wrong from the very start. So, this hypothetical motion we've created does something stunning. Every single point on the sphere moves along its assigned path until it lands at the exact opposite position. The point P moves to the point minus P. This effectively turns the whole sphere inside out, making the outer surface the new inner surface.
Now, to see why that's impossible, we need a brilliant physical analogy. Just imagine there's a water fountain right at the center of our sphere, constantly spewing water out in all directions. We can measure the total amount of water flowing out through the sphere's surface. In physics, this is called flux. Since the water is flowing out, we'll say the initial flux is a positive number.
Let's just put a number on it to make it concrete. Let's say our fountain pumps out 1 liter of water per second. So the initial flux through our sphere is +1. Simple enough. But what happens after our transformation? The sphere is now inside out. From the surface's new point of view, that same water is now flowing inward. So the flux has to be -1 liter per second. It has to be.
And right there, that's the contradiction. You see, the total flux can only change its value if the surface somehow crosses the water source at the center. As long as that fountain stays inside, the net flow has to stay at +1. But remember how we defined our motion? It was based on the perfectly combed hairs, which keeps every point moving tangent to the sphere, and a path around the center. No point ever crosses the middle.
So the flux must change from +1 to -1 because the sphere turns inside out. But the flux cannot change because the surface never crosses the origin. These two facts are in total opposition to each other. We have reached a logical impossibility, a contradiction.
So, what does this beautiful piece of logic actually tell us? Well, it proves something fundamental, not just about spheres, but about the very structure of the space we live in.
The only way to resolve that contradiction is to go all the way back to the beginning and admit our first assumption was just plain wrong. It is impossible to have a continuous vector field on a sphere with no 0 points. That playful puzzle we started with isn't a puzzle at all. It's an impossibility. It's a fundamental law. You really, truly cannot comb a hairy ball.
And that leaves us with one last tantalizing thought. This ironclad law applies to a 2-dimensional sphere living in our 3-dimensional world. But what about other dimensions? Could you comb the hair on a circle? What about a 4-dimensional hypersphere? It turns out the answer changes in this really beautiful symmetric way. But, well, that's a story for another time.